Hey guys! So normally we would just start pH titration curves having finished buffers. I do want to back up a little bit though. It's been a while since we have had class and buffers are part of our titration curves. So I just want to kind of quickly go through buffers and then we'll start with titration curves. This document that you guys are going to see me going through and filling out, I do have posted on Canvas for you. If you have access to a printer and you can print it out, I would highly recommend that, and then you can take notes right on it. If you do not have a printer, that's fine. You can just make notes right on paper. But I do want you to take notes and work through the problems as I work through them. I am going to ask that you at some point take a photo of those notes and then upload them for me. I will have a form on Canvas for you. Hopefully it'll be pretty obvious as to where everything is. And I'm going to use that as attendance. So as I post things on YouTube, I'm going to ask that you do that. Instead of passing around a sheet to sign in, I'm just going to have you take a photo of your notes, upload it on Canvas, and I'm going to use that as our attendance record. I just want to make sure that we're not losing folks. Since I can't see you, I need to have some way to keep track that people aren't falling through the cracks. So please do take some notes so I know that you were here. So buffers. If we remember, buffers were solutions that when I add an acid or a base to it, the pH doesn't change a lot. So what I'm buffering against are large changes in pH. The way that it works is that buffers contain a weak acid and its conjugate base, or a weak base and its conjugate acid. So a buffer solution is actually a weak acid-base solution itself. If we add an acid to it, then the base component of the buffer is going to neutralize it. If we add a base to it, then the acid component of the buffer will neutralize it. And that's how it buffers, right, against large pH changes. You can, of course, exceed the buffering capacity, right? If you add too much acid, then the base has all been neutralized. Adding more acid, the pH will jump down quite a bit. And then the same thing with base, pH jumping up though versus down. Our example here, if we want to look at that, our example, will the following combinations make a buffer? So our question is, are the following combinations a weak acid and its conjugate base? Are the following combinations a weak base and its conjugate acid? The answer is yes to those. Yeah, it can make a buffer. If the answer is no, then, well, no, it's not going to make a buffer. So the first one here, hydrochloric acid and sodium chloride. Again, remember whenever we see sodium chloride, right, if we have a group 1A cation, I'm not going to care about it. So it's the chlorine part that I care. So what we have is chloride, and HCl. So will those guys make a buffer or not? And hopefully you guys are thinking no. And then, of course, I'm going to ask you why. So what are you guys thinking? What's your reasoning for why they will not make a buffer? And it's really weird without your feedback, but I'm going to really hope that somebody is thinking to themselves, they're strong acid, right? HCl is a strong acid, not a weak acid. So this one will not make a buffer solution for that reason. B, I have ammonia and ammonium bromide. This one, ammonia, but then the Br minus, I'm not going to care about that. So what I really have is NH3 and NH4 ammonium, right? And that guy has a positive charge. Why don't we care about it? I assume somebody would ask me. And we don't care about it because it's the conjugate, right, of a strong acid. And we did say that conjugates of strong acids are inert. So if I have HBr, one of my strong acids, Br minus would be its conjugate base. We don't care about it. We cared about chlorine in the first one because it was the only thing I had. I didn't care about sodium, but it wasn't a buffer anyway because HCl is strong, so we could actually say that the chlorine's inert also. So basically our question for B, ammonia and ammonium. And ammonia is a weak base. Ammonium is its conjugate acid, so our answer for this one is yes. How about C? I have acetic acid and potassium acetate. So what are you guys thinking? So acetic acid, I don't care about sodium. So acetate ions, those guys are conjugates. And then the question is acetic acid strong or weak? And hopefully you guys are saying weak. So we do have a buffer solution. The next one, I have phosphoric acid and then Na2HPO4. So because I have sodium, I have two of them. That means our HPO4 has a 2 minus, right? -2 charge because I have two sodiums. And remember, our net charge has to equal 0. So -2 on my conjugate there. These sodiums I don't care about. So I have H3PO4 and HPO4 2 minus. So what do you guys think? Buffers or not buffer solution? So H3PO4 is weak, but HPO4 2 minus is not its conjugate, right? Remember, conjugate bases differ from their acid by 1 proton and only 1 proton. These guys differ by 2 protons. So no, this time our reason is they are not conjugate pairs. Not conjugates. So first one, no. HCl is a strong acid, not weak. Second one, yep. Third one, yep. And then the fourth one, no. While H3PO4 is weak, those guys are not conjugate acid-base pairs. So our next problem here is actually a calculation. So we did one similar to this before spring break, but I do want to work through the entire thing. So first question, it says calculate the pH of a buffer solution, and we're given 0.45 molar formic acid and 0.55 molar sodium formate. And then we're given the Ka of formic acid. So this one is just a common ion problem. I have a weak acid, I have its conjugate. So let's pick a different color here. It's a common ion problem. So we're going to write the acid dissociation equilibrium equation. I'm just going to do acid EQ equation because I'll run out of room to write the whole thing. We're going to make an ice table. I am still totally cool. If you guys can go right to the math without setting up the table, that's fine. You can skip that at this point. Right, we're going to use our Ka because that's what we do when we write our ice table. And then we're going to solve for x. And x is going to be my hydronium ion concentration. Once we solve for that, just take the negative log of it to get our pH. So my ice table, I have formic acid. I do have to tell you, writing with my current stylus is really messy. I do have a new one coming. Hopefully we'll be here next week. Meanwhile, it takes my already horrible handwriting. It makes it a little bit worse, so I'm sorry. This is actually me trying pretty hard. So formic acid plus water. And because it's an acid, we're going to donate a proton to water to get hydronium ions. And then my conjugate base is formate. So initial concentration, I am going to have 0.45 molar. And these numbers I'm just taking right from my original problem. Right, so if I go back up here, I have 0.45 molar formic acid and then 0.55 molar sodium formate. Again, I'm not going to care about that sodium. So that's my conjugate base. So water is not part of my expression, so we can ignore it. Initially, I don't have any hydronium ions, and my formate, 0.55 molar. So that would be my initial concentration. My change, we're going to lose some amount from this side. We're going to call it x. We're going to gain on the product side, so plus x. And then at equilibrium, oops, we're going to get this worked out. What I started with minus what I lost. Guess that was redundant. What I started with plus what I gained. And what I started out with plus what I gained. My Ka is less than 10 to the negative third. It's 1.8 times 10 to the negative fourth. So I can ignore that minus x and plus x relative to my initial concentrations. So when I plug them into my expression, I can just take 1.8 times 10 to the negative fourth is equal to x times 0.55 plus x, but I am ignoring that plus x. We can use that assumption. It's supposed to be a decimal point. Over 0.45 minus x, but again, I'm using that assumption because my equilibrium constant is small. So I'm just going to write that number. And we will solve for x. So if you guys get your calculator out and play along, I'm getting mine out, you can probably hear it. 0.8 times 10 to the negative fourth multiplied by 0.45 divided by 0.55, and I get 1.47, I want 2 sig figs, so 1.5 times 10 to the negative fourth molar. And then to get the pH, we're going to take the negative log of that number. And I'm running out of room. I am keeping the whole thing in my calculator, so if yours comes out slightly different, that's why. Remember sig figs for our log values, it's been a while, that only the digits after the decimal point to the right of the decimal point count. So because this here is 2 sig figs, I need 2 digits after my decimal point. That 3 is coming from my exponent, right? It's coming from the negative 4. That doesn't count for sig figs, so neither does that 3. So my answer down here, it's a mess, is 3.83. So the second part of this problem, we scroll back up so we can see it here. We're going to calculate the pH after 0.1 molar hydrochloric acid is added. So remember, adding acid to the buffer, it's going to react with the base component, right? The base component of the buffer is going to neutralize any acid that we add. So what I'm going to do is I'm going to write that acid-base neutralization equation. We're going to use the concentration of everything to figure out my new concentrations after the base neutralizes that acid. So we're writing what is called the change table. So if we go back down here to our problem so we can work, I'm going to write the acid-base neutralization, calculate the new concentrations. And this is commonly called our change table. So if you're working with someone else and they say write a change table, this is the part that we're talking about. The other part I want to note is HCl is what we're adding, right? Hydrochloric acid is a strong acid. Remember, strong acids are completely dissociated in aqueous solution. So what I have isn't HCl. I have H3O plus, hydronium ions, and chloride ions. And the conjugate base, right, of our strong acid is always going to be inert. It's neutral, so I'm just going to ignore that. So when I'm writing this table, instead of writing HCl, I'm going to write hydronium ions. You can write HCl if you want, but hydronium ions is what I'm going to use. It's actually what HCl is in water. So back up to my problem here. My concentration of hydronium, right, and Cl minus, but we don't care about that, is going to be 0.1 molar. So those are the concentrations I'm going to use. So my change table. I have my formate. So that's the base component of my buffer. It's going to react with my acid that we're adding. So this is my hydrochloric acid. Our neutralization is going to result in a water molecule plus formic acid. My initial concentrations I'm going to write down are the concentrations right from up in the problem. So if we forgot what they are, we'll scroll back up. So formic acid, which is going to be on my product side right now, is going to be 0.45. Formate, which is on my reactant side, 0.55. And then hydrochloric acid is 0.5. So what did we say this was, 0.55? This is 0.10. I'm still just going to ignore water here. And then this is 0.45 molar. So our change then, it's essentially a limiting reactant problem. Because my coefficients are 1 to 1, whichever of my two concentrations is smaller is going to be my limiting. So I'm essentially going to take the smaller of my two reactants, which is going to be the 0.1, right? 0.1 is smaller than 0.55. And I'm going to subtract that from both of my reactants. And then I'm going to add that to the product side. So I'm going to lose 0.10 molar. I'm going to lose 0.10 molar. And I'm going to gain 0.10 molar. And then we're going to write our new concentrations. So again, you're just taking the smaller reactant, subtracting it from both of the reactants, and then adding it to the product side. Right? You can never lose more than your smaller amount. If I only have 0.1, I can't lose 0.55, right? It has to be the other way. So 0.55 minus 0.10 is 0.45 molar. This goes to 0. And then 0.45 plus 0.1 is 0.55 molar. The next thing we're going to do is we're going to essentially do part 1 again. So it's a common ion problem, but we're going to use the new concentrations. So you would write the ice table again. So you'd write your acid dissociation. I'll see if I can write this really small. Q, ice table, etc. So ice table, I'm going to start with my formic acid. It reacts with water, right? Remember, anytime we write our acid dissociation equilibrium equation, it's always the acid reacting with water. I'm going to hydronium ions plus my conjugate base, formate. Concentrations now are coming from my change table, right? We're using our new concentrations, So this is 0.55. Don't care. 0 and 0.45. I'm gonna run a room here, so I'm just gonna do the minus x plus x stuff. So I would do minus x as my change, and now what I'm doing is I'm writing my equilibrium concentrations. So this is going to be plus x, so we'll just write x when we do it, and this is plus x. My Ka is still small, so I'm still going to ignore that minus x and plus x. And again, if you can keep these numbers straight without actually writing the equation and going right to the math, you can. I'm fine with that. I will show you, we're going to, in a few minutes, do the Henderson-Hasselbalch equation. If you remember, we did that real quickly at the end of class before spring break, but we'll do that again. If you use that equation for buffer solutions, then you can just eliminate the ice table. But for now, 1.8 times 10 to the negative 4th, that was my Ka. That's going to be equal to my concentration of hydronium, which is x, multiplied by 0.45. My concentration of formate, again, we're ignoring that plus x, divided by my concentration of formic acid. And then we need to solve for x, which is going to be my hydronium ion concentration. So calculators, 1.8 times 10 to the negative 4th, multiplied by 0.55, divided by 0.45. And I get x is 2.2 times 10 to the negative 4th molar. pH would be the negative log of that. So negative log Make sure you use log base 10 and not natural log. And I get 3.66. So 3.66, if I compare that number to what my pH was before we added acid to it, 3.83. So it did go down a little bit, which we expect because we're adding acid, right? My pH is smaller as my hydronium ions increase. So my pH went down, but not a lot, just a little bit. So our buffer's working. So part number 3, go back up here to our problem. So number 3, we're calculating the pH after 0.1 molar sodium hydroxide is added. So we're adding it to the original buffer solution. So essentially we're pretending we didn't do number 2. So we're taking the original buffer, we're adding 0.1 molar sodium hydroxide to it. We're not going to care about the sodium, right? Sodium hydroxide is a strong electrolyte. It's going to be completely dissociated in aqueous solution. Group 1 cations are inert, so we're not going to care about that. So I'm going to write a change table again, and it's hydroxide that I'm going to use. So I'm adding 0.10 molar hydroxide ion, if we want to think about it that way. Because this is a base, it's going to react with the acid component. So when I write my neutralization equation, it's going to be the formic acid reacting with my hydroxide ions. We're going to make that change table again. We're going to calculate our new concentrations and then go back to the ice table. So down to where my work is. So we're going to write the acid-base neutralization equation. So remember my hydroxide is a base, so it's going to react with the acid component. So formic acid plus my hydroxide ions. And that's going to go to a water molecule. It's always going to be one of our products. Plus my formate. My initial concentrations for these are just going to come right from the original problem. Try not to make you guys dizzy here with all this scrolling, but I'm going to go back up. So it's still the 0.45 for formic acid, 0.55 for formate, and then 0.1 molar for my hydroxide. So 0.45, 0.10, don't care, 0.55. And then again, limiting reactant problem. So we're going to take the smaller concentration of the two reactants, subtract it from both reactants, add it to the product side. So because 0.10 is smaller than 0.45, that's the one we're going to subtract from both. So take the smaller, subtract it from both, add it to the product side. Always subtract from the reactant side, always add to the product side. So my new concentration of formic acid is 0.35 molar. This is going to 0, and this is 0.65 molar. So again, this was my change table. And that gave us our new concentrations. We're now going to calculate our pH using those new concentrations, doing the whole ice table thing again. This girl first. So ice table, first thing we need to do is write our acid dissociation equilibrium equation. Remember, that's always acid plus water. That's going to hydronium ions plus my conjugate base. My initial concentrations are my new concentrations, right? We're using the new ones. So that's coming from my change table above. So 0.35, not part of my expression, 0, and 0.65. We're going to lose x, gain x, gain x. 0.65 plus x, though I am just going to ignore that x, and 0.35 minus x. Again, I'm just going to ignore that x. My Ka is the concentration of products, so x times 0.65 minus, or plus x, sorry, ignoring that because my Ka is small, so we can use that assumption, over the concentration of my reactants. Again, because my Ka is small, I can use that assumption to ignore that x, right? We're saying that that x is negligible compared to my initial concentrations. We're going to solve for x, and x is going to be my hydronium ion concentration, right? If we look, x is hydronium ion concentration. So calculators, oops, so I dropped mine, sorry guys. 1.8 times 10 to the negative fourth multiplied by 0.35 and then divided by 0.65. And I get that x is 9.69, so 9.7 times 10 to the negative fifth molar. And then pH is going to be the negative log of that number. And I got 4.01. Again, remember sig figs for our log values, right? Only the digits after the decimal point count. So I need that 0.01 to get two significant digits. That 4 isn't going to count. Kind of looking at our values, 4.01 is what I get after I've added some base to it. We go back up here, we started out with 3.83. So again, my pH went up a little bit, which it should, because we added base, right? Hydronium ion concentration went down, hydroxide ion concentration went up, but not a lot, right? It's being buffered. So one more part to this problem, and then we'll be done with it. I go back up. And the last part wants us to compare the pHs from step number 2 and 3 as if added to water instead of the buffer. So we're saying, what would the pH be if we added a 0.1 molar hydrochloric acid solution to water instead of buffer? What would the pH be if we added a 0.10 molar sodium hydroxide solution to water versus the buffer? We just kind of want to compare what would happen if we added that to something that wasn't a buffer solution. So we're going to go back down here. And I do want to write down my buffer numbers, so 3.83, you guys can help me remember them, 3.66 and 4.01. So let's just write those over, not highlighter. So what did I say it was, 3.83? 4.01 I can see, and 3.66? I think that's right. Let's double check. You guys actually can't help me. There we go. Okay. So I just wanted to put those there because we'll compare how it changes when we add it to water. So water, before we add the acid or the base to it, what would its pH be? If I just have pure water and I haven't added anything to it. I'm really hoping you guys are thinking 7, right? If it's just pure water, my hydronium ion concentration is equal to my hydroxide ion concentration, which is equal to 1.0 times 10 to the negative 7th molar, right? That was based on our Kw, our ion product constant for water. So if it's just, pure water, it's just a neutral solution, then hydronium ion concentration is actually equal to hydroxide. And then because those two multiplied by each other are equal to 1.0 times 10 to the negative 14th molar at 25 degrees Celsius, that means hydronium ion concentration is equal to 1.0 times 10 to the negative 7th molar. Negative log of that, we get a pH of 7.00. So kind of our equivalent number to the 3.831 would be 7.00. So just water itself. And then the HCl one, remember that hydronium ion concentration is equal to my strong acid concentration. So hydronium ion concentration is equal to 0.10 molar. Take the negative log of that number. Sorry guys, technical difficulties here. And I get 1. 0.00, of course, we get the right number of significant digits. For my sodium hydroxide, right, this time we can do, this is one we can do 2 different ways. I can calculate my POH, or I can use my my KW, right, my ion product constant for water to determine hydronium ion concentration. Either way, hydroxide is equal to my strong base concentration. I'm going to put a little asterisk on there though. Remember, if it was one of the strong acids where I have 2 hydroxide ions for every 1 cation, then you do have to double it. Since this is sodium hydroxide, I don't have to do that here, but just remember this isn't always necessarily true. So that's going to be 0.10 molar. I'm going to do the POH version. So if I calculate my POH, it's equal to 1.00, right? Negative log of 0.1 molar. And then my pH would be 14.00 minus my POH, which gives me 13. So kind of comparing, we're starting out with 7. I had the same concentration of acid and my pH jumps all the way down to 0.1, right? When I had my buffer, we started out with this 3.83, and then I just jumped down a little bit, right? That's a small change compared with 7 going down to 1. And then when we added base to it, I jumped from 7 all the way up to 13. When we added it to the buffer, I just went from 3.83 to 4.01, so a small change. So dramatic changes if I add it to water, small changes when I add it to my buffer.